April 26, 1986. A nuclear reactor explodes in the Soviet Union. Most people believe Chernobyl was an accident. It wasn't. It was the predictable result of a system that was unstable by design. This is not a story about radiation. This is a story about engineering decisions, ignored warnings, and a reactor that could not behave safely under stress. Chernobyl did not fail in a second. It failed for years before the explosion. Chernobyl used an RBMK reactor design. It had two critical characteristics. 1. A positive void coefficient. 2. Graphite-tipped control rods. In simple terms, when water inside the reactor turned to steam, reactivity increased instead of decreasing. In most reactor designs, steam formation slows the reaction. In RBMK, it accelerated it. That means instability was built into the physics of the core. Now add the second flaw. The control rods were designed with graphite tips. When inserted during an emergency shutdown, they initially increased reactivity for a short moment before reducing it. The emergency brake first pressed the accelerator. That is not a small mistake. That is systemic design negligence. On the night of the accident, engineers were running a turbine rundown test. The goal was simple. Could the spinning turbine generate enough residual power to supply emergency pumps before diesel generators started? The test had failed before. Instead of redesigning the system, they tried again. Power levels dropped too low during preparation. The reactor entered an unstable operating region. To compensate, operators withdrew most control rods. This violated safety regulations, but they were following production pressure. The system was now operating in a state the reactor was never stable in. Low power, high xenon poisoning, minimal control rods inserted, an unstable core waiting for disturbance. The test began. Steam production increased. Because of the positive void coefficient, reactivity increased, power surged. Operators pressed AZ5, emergency shutdown, all control rods inserted at once. The graphite tips entered first. Reactivity spiked sharply. Power increased violently within seconds. Fuel channels ruptured. Steam explosion. Graphite caught fire. The reactor had no containment structure. The core was open to the atmosphere. The explosion was not random. It was the direct mechanical result of a flawed system meeting human pressure. The explosion was not the real failure. The real failure happened long before. Engineers knew about instability at low power. The positive void coefficient was documented. The control rod design flaw was known. Previous incidents occurred in other RBMK reactors, but the culture did not allow design criticism. Safety warnings were suppressed, production targets were prioritized, reactor flaws were classified. The system was optimized for output, not resilience. Chernobyl was not a human error. It was a systems engineering failure. Chernobyl is not about nuclear power. It is about ignoring low probability instability, operating systems near unsafe margins, silencing engineers under management pressure, designing emergency systems that introduce new risks. Today, this happens in aviation software, automotive electronics, energy infrastructure, large-scale manufacturing. When optimization removes safety buffers, systems become fragile. And fragile systems do not fail gradually, they collapse. Chernobyl teaches one brutal lesson. If physics allows instability and management allows pressure, failure becomes inevitable. Engineering is not about making systems work. It is about making them stable under stress. Chernobyl was not an accident. It was a design waiting for a trigger, and every unstable system today is waiting too. This is how systems really fail.